the Technical Information Scientist of the Jackson Laboratory. My name is Pete, and my job as a Technical Information Scientist is to serve the research community by answering all mouse-related questions. For any of you watching live, you can use the comment section of the video to tell us where you're viewing from and any related questions you have, and we will try to answer those live. So today, let's talk good, bad, and ugly genotyping gels. To help me answer your questions, I'm joined by my colleague Jen, the manager of our model generation genotyping core.
Hi, Pete.
Hi.
Yes, I'm one of the managers of the model generation genotyping core here at the Jackson Laboratory. Specifically, I manage the group that designs genotyping assays and validates them. And we design and validate thousands of genotyping assays per year.
All right. So when researchers are genotyping JAX mice and they struggle to get the assays to work as needed, they frequently then reach out to TIS to help them troubleshoot the assays. In these situations, we're frequently asked if you actually need to use the same exact PCR reagents as we do to get the assays to work. And the answer to that is you should be able to use your own regular PCR reagents using our primers, but you may need to optimize the assay. We also commonly get people who describe the results over the phone or in emails, or they even send us their gel pictures, but they're not able to understand how to actually interpret those results such that they can determine what went wrong and how to fix it. So what we're going to do today with Jen's help is to review a variety of gel pictures and then discuss what the problems are and how to make the proper adjustments. And to help us along, my colleague Sarah is going to play the part of a customer and show us her genotyping gels.
Pete, I'm so glad you're there. I have all these gels that I need your help interpreting.
All right, well, let's see what you got.
All right. I have a couple gels I want you to look at for me and tell me what you think. So I want to start with the ones that I thought worked all right to see if I did things right to begin with. So I have a couple gels where I was running, they look pretty good to me. I felt pretty comfortable calling the samples, the ones that were heterozygous versus my wild type. I made sure I included this control just to be safe. What do you think?
I mean, it looks pretty good. It's easily scorable. I see you also have a water control, which
Yep.
has no amplification, which is really good. Your ladder is appropriate and everything looks very well.
Spaced.
Yeah, spaced, and the bands are nice and sharp, which means you ran everything appropriately.
Yeah.
Good.
Absolutely.
And I had this one where I'll admit, I was struggling to genotype the mice. So I wasn't sure what to do. I looked up a couple things online and I found recommendations of changing magnesium chloride or changing concentration of DNA. So I tried that. Is that the right way to go?
That is absolutely one way to optimize an assay when things are not working. And there are others that we will also discuss. There's not always a one answer for that covers every situation, and a lot of it depends on what it looks like. But what you can see there where you have it in red, you can see both bands. You might like that upper band in the heterozygote to be a little bit more robust, and we'll talk about some ways that we could do different optimization now that you've fixed on the right magnesium and DNA concentrations to improve that and optimize it further.
All right. Well, I have some that don't look quite as good. So tell me what you think about these. This one, I'll admit, I kind of forgot the water control, so I'm not sure what they are, and I'm not sure what these samples are here.
Right.
So Sarah, can you tell me what size of amplification product were you attempting here? Because one of the problems I'm seeing is the ladder is not clear at all. So I would have a hard time even saying what size of amplification product I think that is.
Okay.
And you really don't get any clarification on whether there's a single product there or more than one?
It's just one. I only ran, so it's for a Cree, and I only ran 2 primers that just amplify the Cree. And that's the case for this one and for this one on the far right. They're only amplifying Cree. I didn't have any other expected bands.
I see.
Also, since the bands don't run very sharp, it may be that you didn't run the right agarose concentration or use the right voltage, because
Okay.
everything's sort of diffused a little bit. So it's really hard to be real clear on what's going on.
Yeah.
All right. And this one, I felt okay about it, but is there anything that I should consider?
Oh, again, the latter is really important here, isn't it? So, I'm seeing a couple of things that are sticking out to me. So your KOMP positive, that is your known heterozygous control.
Yep, that's my known heterozygous control.
And then your negative is showing a band?
That should be, well, this one is not a CRE, so this is my
It's a wild type control.
Wild type product. So I think that actually looks pretty nice, except for the ladder.
Okay.
Yeah, so preferably with your ladder, you want at least one of the ladder bands lower than your smallest band, and at least one bigger than your biggest band, so you can make sure that they're accurately sized on what you would expect them to be.
Okay. Well, I'll admit, I really wasn't sure what to do about these. I honestly didn't know what happened here. I ran it. I mean, I do the same assay all the time, but all of my samples just looked like that for this one particular assay.
I mean, it could be degraded DNA. It could also be that you have way too much template DNA. A lot of people don't realize that if you have too much template DNA, it can often cause the reaction not to give you the bands you want because you use up your primer much, much faster. And that what you're seeing may actually be the genomic DNA because you really overloaded those.
Okay, all right. And here, I wasn't sure what's going on down at the bottom here. It was so bright, but it was very fuzzy, so I wasn't sure what to kind of interpret for this part of this gel.
Those are classic primer dimers. And so anything that you see, smaller than 100 base pairs is almost, and is fuzzy like this, it's not showing any sort of clear product. Those are primer dimers.
Okay.
Which is when the primers themselves anneal to each other and produce a product, right?
And is there anything that you can do to prevent that from happening? Or reduce it?
Yeah, so you can address it by your primer concentration. You can also, so your concentration of primers. Given that you're seeing results here, so your primers are amplifying your product of interest. I don't necessarily think that you need to necessarily redesign these primers. But there are certainly primer programs that take into account the possibility, do a really good job of looking at possible dimerization. I use Primer 3 for almost everything, and it does a really nice job with that. If you weren't seeing good, robust amplification and you were seeing these big, a large amount of primer dimers, I would certainly consider perhaps redesigning the primers. What do you think, Pete?
I think that's right. It really depends on how well it's working and if the gel is scorable. I mean, if it's scorable, the fact that you get primer dimer and it doesn't interfere, I don't know, it doesn't look as pretty, but if it gets you the data that you need, it's not something you would have to worry about.
And I see that we do have some questions from people watching who are also very interested in learning about genotyping. So you mentioned previously with this particular one about potentially voltage issues or gel percentage. Is there a recommended gel percentage or voltage that people should use, or how do you make those decisions?
Well, the percentage depends on the bands that you're trying to separate and amplify. And frankly, you can probably just Google. There's lots of guides. Anybody that makes agarose or PCR products will have guides on what percentage agarose to use based on the bands that you're trying to separate. The voltage will depend on the distance between the electrodes, but also sometimes the gel percentage, because the higher the voltage, the hotter it gets, and then you can melt the gel. So if you have a really low percentage, you don't want to run as high a voltage. And there are, again, formulas to look at the distance between them. And so there's no one answer. Again, it depends on the bands you're trying to separate and the apparatus that you're using. But all of that information you can find online.
If your
All right.
products, if your products are pretty close in size, you're going to want a higher percent agarose in your gel.
Mhm.
And so something like a 3% gel, if you were looking at a product, say, that was has maybe a 10% difference in size. So maybe if you were looking at 450 base pairs and 500 base pairs in the same reaction,
Mhm.
I would say anything less than a 10% difference, you should be looking at, you want to up, you want a 3% gel. Start with a 3% gel. What do you think, Pete? Is that fair?
It is. The other thing that I did back when I ran gels is I would always look at my ladder, and
Mm.
basically I would look at the bands that the size of the products I'm trying to separate, and then go back through my notes and find a ladder that those bands turned out really well that are going to be just above and just below, and then what percentage and voltage I ran. So you can basically accumulate experience with all of your equipment as long as you take notes on what voltage you ran, for how long, what percentage gel. Then you can go back and use your ladder and say, wow, that's what I want to recreate because my bands are right in between these two ladder bands. And then you just do that again.
Mhm.
But I think in general, roughly, a 1% to 3% agarose concentration is
Pretty
the
standard.
range that you're going to be working in.
Yeah.
Okay. And you mentioned with the primer dimers, changing the primer concentration. Is that specifically reducing the primer concentration for primer dimers? Or would you ever increase the primer concentration?
I
So it's
think it
gonna
may depend on what bands are showing up and what bands
Okay.
are not.
And
We're gonna talk
we
about some
talked about that.
situations where
Yeah.
you want to manipulate the primer concentration
Okay.
to get better results.
All right. And I want to get to the end of, I have a couple more to show you because I really need your help, Pete. You're my only hope. I have this one where I'll admit I did score it, but then afterwards I thought back whether I could score this, whether I could actually make the decision, differentiate between the wild type and the hets. Because even though I've run this assay so many times before, for whatever reason, this time I got all these extra bands in the middle, and I don't usually get that. So can you help me understand what might be happening here?
I mean, they're what we would call artifact bands. So they're bands that get amplified, but aren't the bands that you're expecting to. And just realize that your primers are going to anneal to many different places in the genome, and they can amplify a product. And what I would say is the same as what we talked about with primer dimer. If you have the proper controls and you can appropriately score the presence of artifact bands, again, it doesn't look as good. But if you can score it appropriately, then the presence of artifact bands is just an annoyance in terms of how it looks, but not going to interfere in what you're trying to accomplish.
Yeah, I agree, Sarah. I think if you had your appropriate controls on here, if you had a wild type control, a previously typed het, and you absolutely could be sure that those bands in between were non-specific for this assay, those are scoreable data. I don't love the ladder here. I'd like to, absolutely be able to say that those bands are the size that you're expecting to see, because the question you have to ask with a ladder that's fuzzy is maybe it's the second band or the third band. You don't know which one is the mutant product in this case. But if you had a nice clean ladder, I would feel okay scoring those data.
All right. I got one more I'd like you guys to look at with me. I felt pretty okay with this. Again, the first time I looked, I had a floxyl up here, and then I had my Cree on the bottom, all the same samples. And then I was looking at these, and I realized that my water lane had something, but it was so faint. And I was just wondering, is that really, is it okay still to score this, or what do you think?
Anytime something shows up in the water lane where you should get no amplification, I would always be concerned. There's multiple possibilities of how that happens, but what you have to worry about is contamination. So either your DNA got contaminated or one of your reagents is contaminated with DNA that carries the Cree transgene. And so then if that's the case, then which of these samples can you be confident on? The ones that are really bright, and ignore the ones that are faint. I mean, now you're left with ambiguous data.
Yes.
Which ones are real and which ones are not.
I
And
agree.
so, yeah.
I agree that this needs a rerun. And
Yeah.
and what I'm looking at here, and when we're talking the water control, just so everybody is aware, or is otherwise called a no template control, is it contains the reaction. It contains all of the components of the PCR, but does not contain DNA, sample DNA. And so you're testing for whether or not you have amplifiable DNA in that sample, and you don't want amplifiable DNA in that sample. It's supposed to be your negative control. In this case, you can look across these samples and say, well, I see one clean result sort of in the middle. Maybe this isn't contamination of the reagents. It's contamination of the plate, maybe. When you were setting these all up, you had some aerosolization happen, droplets fell onto your plate that you were setting up. Or maybe you just didn't get DNA into that particular well. But I would say, you need to rerun this. I wouldn't want to make a call on what are true here, which are true positives and which are not.
No. And with that, what we would highly recommend to cut down on contamination issues is do all of your DNA extractions and PCR using filter pipette tips.
Absolutely.
To prevent that aerosolation and cross-contaminating one sample with another or one tube with another.
You should also separate your workspaces. You shouldn't be setting up your PCRs in an area where you handle post-amplified product. So you should keep your amplified product separate, in a gel room area or wherever, but where your setup is happening, you want that to be clean. And you can be looking at filter tips, like Pete said. There's also a product called DNA Away, which is very nice. I've used it a lot. It will clean up your workspace, your pipetters. You can rub it on your gloved hands, but you do need to be careful. You need to let it completely dry, and you don't want to get it into any of your DNAs, because what it's going to do is eat away. It's going to not make it amplifiable. So be very careful with DNA Away, but it is a tool in your toolbox.
Okay. Well, those are all of mine, but Jen, do you want to go through some other examples of things to think about or be concerned about? I should say we've only got really a couple minutes. We might want to go through a little bit.
This is a good one, though.
Yes, yeah. This is important, because you say, what's going on when I don't see amplification? And the important thing here, and I don't think that Pete and I can stress this enough, you need to be running your controls. They really provide you with a lot of information here. So in these two cases, you can see the gel on the right shows nice amplification from the two samples at the end, which are wild type controls. These are wild type controls that we use all the time. We know they work. So that's a nice thing. You want to use wild type controls have worked with other assays. Mm-hmm. In this case, you can see how well these wild type controls work. So you can make some conclusions about what happened here, right? It's not the PCR. It worked fine. It amplified what you expect from your wild type controls. So that leaves you with, you've got a problem with the samples, right?
Yep, exactly.
Whereas if you go to the left and you look at the two wild type controls there are two of them, and then two heterozygous controls, they're not amplifying well. And if you know that these are wild type controls you've used in the past and they're reliable, then you can make conclusions about, this is something else. Maybe, less likely that it's a DNA problem, and more likely that you have something wrong with your reaction cycling situation. So Pete, do you want to sort of talk a little bit more about that?
Yeah, I mean, the reaction itself, somewhere in the failed. So the primers are a problem, or one of your other reagents is the problem, or there's a problem with your thermal cycler.
Right.
As long as, again, that controlled DNA, and if you talk to us enough, control, the right controls, and especially, as you mentioned, a wild type control that you already know has worked with another assay. So much information, because with these two situations, one, we're looking at the DNAs, the other, we're looking at the other reagents. So now we've eliminated, for each of these situations, things to look at to try to fix. And that's what information we get from these gels, and the fact that you've used appropriate controls. If we see a gel that just has all your samples and no amplification, the first question we'll ask you is, what happened with your controls? And if you didn't run them, that's going to be your first job, is to go back and rerun it with the controls, because this information basically tells us where the problem is, or potentially where it is.
Also, one thing I do want to point out is, don't ignore your thermal cycler. Make sure that it's getting routine maintenance. It's an important part of genotyping. Make sure that they're in tip-top shape, that the annealing temperature that you expect it to be at is what it's actually hitting, etc.
All right. Well, I think we actually only have time for probably about 2 more slides, but why don't you guys talk about this one? I think this one's a fun one.
We can run through this one pretty quickly. So this was a same individual set these up. These are the same samples. The only thing that's different is the thermal cycling program, the extension time. So you can see that when the extension time was longer, so in this case, the upper band is about 600 base pairs. When the extension time was changed, it gave that product, that mutant product, the ability to realize its potential here. So you can see pretty easily that any tweaks in your thermal cycling program can make a difference. And let's go on to the next one, because there are a couple other very important ones I want to point out here. This one's important because, especially if you're new to PCR, you have to recognize you may not be great at using a pipetter. And we see this with new genotypers all the time. So if you look at the bottom gels, that bottom gel, these are the same samples set up in duplicate at the same time, same person, same reagents. And you can see that they had a bunch of dropouts. If they wouldn't have set this up in duplicate, which I strongly recommend, especially if you're new to genotyping, that you set up your reactions in duplicate, we would have not been able to figure this out as easily as we did because they were set up in duplicate. This was a pipetting problem. So definitely a good idea to do that. Pete, do you want to talk about the upper gel?
Well, I'd rather go to the next one if we're going to talk about primers. I think that one is a better one here. So I think that's what you were getting at, is here where we have one band outcompeting the other band.
Yes,
so
and this is a very common problem, isn't it?
Very common. So what you'll see is that in the highlighted sections, those are the duplicates. So the top and the bottom are essentially the same samples. And what you'll notice is in the left-hand side of the top, you see 2 bands, but on the bottom, you only see one of those bands, which means the upper band is just not amplifying as robustly. So the question then is how many of these you can actually call correctly. Yeah. And so this is a common PCR problem, is where you're supposed to amplify 2 bands. One of them amplifies better and the other is faint or absent. And the way to deal with that is to manipulate the primer concentrations. So that you can basically, for the band that's not amplifying well, you can increase the amount of that primer or those primers specific for that. You can decrease the primers that are amplifying well, or do both at the same time. And you can then basically run all 3 of those scenarios and see with your controls, again, which show the bands as you need them to see well, so that you can appropriately score your gels.
If this is a 3 primer or 4 primer assay, you can separate out wild type only and mutant only, and then put those data together to get your final genotyping results.
Yep.
In this case, what's interesting about it is the wild type product is the lower product and the mutant product is the upper product. And you could call your homozygous mutant animals off of this gel. I would feel fine with that because the lower product is preferred. You know it would be there with that upper band amplifying as well as it is. So I think you could call homozygous mutant animals here. I would not call either wild type or heterozygotes because you simply can't tell what's going on with that mutant product in the presence of the wild type allele. So you need to make some changes as you suggested, or you can go ahead and run this instead of this multiplexed as a multiplexed PCR, you can run it as a separated PCR. And last slide.
Last slide, I think we can go pretty quick. It's another discussion of artifact. But
I love this one, Sarah.
Yeah, what I love about it is that, you know, my first glance at it when I was looking at this was like, oh wow, that's a lot of nice heterozygous samples right there.
Look at all the pets you have.
Heterozygous samples.
You have lots of pets, right? And isn't that great? Except the problem is, look at your het control.
Right up
the
there.
red box.
And my wild type.
And your wild type control. So your wild type band is the lower band, as shown in that heterozygous control, and your mutant band is the upper band. And so when you look across at the samples, you're actually looking at homozygous mutant animals. You're not looking at heterozygotes. That small band, which is running about 100 to 120 base pairs, it's a background band. You can ignore it for this assay. And I would feel perfectly comfortable scoring these animals as homes with as well as the two bands amplify in the known het. So you want to be very careful. Again, ladder. Make sure the ladder's nice and clear. Make sure you're running the appropriate controls and you'll be set.
Yep, exactly.
All right. Well, I think we're just about out of time. We went a little bit over, but gosh, we're having so much fun. So any last thoughts, Jen and Pete?
No, we cannot stress how important it is to run the appropriate controls. And I know in the we should have provided you a link to that genotyping resource. There's a whole section on troubleshooting, and that's the first thing we talk about is what are the appropriate controls for what, because everything comes down to what do the controls look like, and that is going to help you figure out what information you can get from the gel and potentially what you need to do to fix the problems that you have. It all comes down to how the controls look.
Yeah, and I would just say, strive for your best data. I mean, really optimize these assays so that they're good workhorses for you and you don't have to guess. And I know it can be frustrating, especially if you're new to genotyping, but it's well worth taking the time and effort to become a subject matter expert. It will save you a lot of problems down the road if you can accurately and define your mice.
And I can just make one more tiny point. Tried to get to a lot of questions, but we had so much to cover. So any questions we didn't get to in the comments, please reach out to us at micetech@jax.org. And we'll be happy to answer any additional questions you have.
Good luck, everybody, and you can do this.
Absolutely. So thank you for joining us this week. Our next MiceTech talk is called Let's Talk New Data on Old Mice, which will be live Tuesday, February 2nd. We look forward to seeing you on LinkedIn and YouTube. This is Pete.
Jen.
And Sarah.
Saying stay healthy, stay safe, and stay excited about research. Thank you.
Thank you.